Hello and welcome to IB in A-Level Learning Center, and this is Mr. Tai. In this video, I would like to explain a question in AP Physics 1, 2026, free response question number 4. This is the question. Toys X and Y are free to rotate with negligible friction about a vertical axle through the center of each toy. Here, they are shown on the diagram. Okay, this is the center, the axle. The upper portion of each toy has a radius R0, which is this length from the axle to the edge of this upper portion. As shown the side view in figure 1, and of course the radii of the two toys are the same, which are R0 here, okay? A string of length L0 is completely wrapped around the upper portion of each toy. The rotational inertia of toy X is Ix, and the rotational inertia of toy Y is half of Ix. So the second thing on the right, toy Y has half moment inertia, rotational inertia, okay? Toys X and Y are initially at rest. A constant horizontal force of magnitude F0 is then exerted on the string of each toy, which causes the toy to rotate as shown in the overhead view in the figure 2. The axle, okay, the figure 2 down here, it rotates in the clockwise direction when we view from above, okay? The axle of the toy remains vertical as the force is exerted on the string. This is an important thing. Because we cannot solve the problem when the toys, they are not stable, they ziggle, they tilted, and the axle of rotation is not perfectly aligned vertically, okay? The string do not slip as the force exerted on the string does not slip, which means that the distance the distance that a point on the toy rotates is the same as the length of the string unwinds, okay, unwinding. In other words, the angle that the two toys rotate is the same as the no, not the angle. Just remember that the circumference, the distance that one point rotates, is the same as the length of the one point on this upper portion of the toys rotate the same distance with the length of the string unwinding, okay? When the string loses contact with the axle toy X, the angular speed of toy X is omega x. When the string loses contact with the axle of toy Y, the angular speed of toy Y is omega y. Part A indicate whether omega y is greater than, less than, or equal to omega x by writing one of the following identity inequality or equation: omega x equal omega y. Justify your answer using quantitative reasoning beyond referencing equation. Okay, I will write the answer later, but here the way we understand the problem, we need to identify which angular speed is greater. Angular speed relate to these things. It relate to the work done by the torque, or we have the speed, angular speed. Let's write omega equal omega 0 plus angular acceleration alpha multiplied with the time. It is similar to the formula V equal U plus AT, okay? But in this question, we don't know time. The time is not given. Therefore, we use a different formula, omega square equal omega 0 initial speed square plus 2 times alpha angular acceleration multiplied with the angle that it rotates when the speed changes from omega 0 to omega. it started from rest, which means this omega 0 is 0. Okay, this equation, which is independent of time, actually derived from the energy relationship 1/2 I moment inertia, rotational inertia, multiplied with omega square, which is the final rotational kinetic energy, minus 1/2 I omega 0 square. This is the change in rotational kinetic energy in case that there is no linear translational kinetic energy. Nó không có động năng tĩnh tiến mà chỉ có động năng quay thôi ha. Rotational kinetic energy. This change is equal to the work done by the torque, which is the torque T, the total torque, okay, multiplied with the angle that it rotates. It's similar to the translational kinetic energy change, delta K equal the 1/2 m v final square minus v u initial speed square, which is the change in kinetic energy. Okay, so I'm reminding you about the similarity between rotation and linear motion. Okay. Let me close everything. No. So we will use this equation to justify which angular speed of the toy y or the toy x is greater. Okay, the key is that the angle theta that they rotate is the same for both toys, because that angle theta is the ratio between the length that it rotates, one point on the upper portion of the two toys rotate. That distance is L0, which is the maximum length of the string unwinding. Okay, when we pull the string when the string is totally unwind, here, this is L0, okay? And we divide the radius R0, which is the distance from the point of contact between the string and the upper portion. This ratio L0 over R0 is the angle, which is the same for both toys, okay? And alpha, another key idea, angular acceleration is the torque total acting on each toy divided by moment inertia I. Okay, the torque here T will be the same torque, because that torque is the force, which is the same F0 multiplied with the perpendicular distance from the axis of rotation to the force, which is R0, the radius of the upper portion. Okay, so the alpha is different depending on the moment inertia I. Okay, we know that I y is half of Ix. The torque is the same, so half Ix means the alpha of y will be twice the alpha of x, because according to the upper formula here, the angular acceleration is inversely proportional to I, rotational inertia. Okay, therefore when the rotational inertia is halved, the acceleration is double. Okay, so one more time, omega 0 is 0, the angle is the same, the alpha of y is different. So let me write a conclusion. Omega square is therefore directly proportional to alpha, because angle is the same. Okay, which means omega is proportional to the square root of the acceleration. The y has a greater acceleration. Let me highlight this in different color, blue color, green color. Okay, this one. The second toy y has twice acceleration. Therefore, the speed omega, the conclusion, the omega of y will be greater than omega of x. So this is the mathematical derivation of the answer. Okay, of course, because the question asks us to explain the reason without using equation, so we're gonna write a paragraph to explain that. Okay,